All right. Where were we? We were counting up the subatomic particles, correct? I think this is where we ended up. All right. All right. So this is the periodic table. We'll spend quite a bit of time talking about this. This is an amazing tool. And I always look at the periodic table in great amazement and really admiration of God. I look at this and think God gave all these elements to us, and we get to discover them and how to use them. I think it's absolutely amazing. I I will completely admit I do not have all the symbols memorized. Uh, I probably should, but I don't. I talked to my wife, who's also a chemist and a much smarter chemist than I am. And she said, yeah, I don't have them all memorized either. I did memorize them in 10th grade in high school. But at that time, there's only 30 elements that had been discovered. So come on, that's kind of funny, isn't it? All right, I lied. There's only 20. All right. Amazing thing is, you look at the left-hand side of the periodic table, these are going to be your metals with the exception of hydrogen. The purple line is going to be the metalloids. Those are the ones that can have both metal and non-metal metal characteristics. These are going to be the non-metals. These are the lanthanide and the actinide series. Uranium is the last naturally occurring element on the periodic table. Everything after uranium are made in nuclear reactors or in super heavy element colliders. Likewise, there as well too. Technetium actually does not naturally occur. That is actually made in nuclear reactors. It's used for medical imaging. Certainly, if you're going to look at somebody's gallbladder, it would do that. I had that done once. I have an intestinal disease, so I went to a hospital a number of years ago. That's actually quite sick, and they they put technetium into an IV, and it's a very unique experience. I'll tell you, it's you swear once it hits that bloodstream, you swear you wet your pants. It's bizarre. I remember looking up, she go, oh nope, I didn't pee my pants. I was kind of a neat thing. So there's actually 91 naturally occurring elements on the periodic table. Yeah, but everything after 92, after uranium, it is man-made and usually typically very short lifetimes. They're going to be grouped in columns based on their chemical and physical properties. Here are the alkali metals, the alkaline metals. Here are the halogens, the noble gases. These all have names. We're not going to be too worried about it. My personal favorite column is going to be the coinage metals, copper, silver, gold. So I kind of like them. Remember at a previous job, they would always put the professor's pictures on the board out in the hallway. What's your favorite element? Oh, carbon and phosphorus. Heck, gold, baby. Are you kidding me, man? Hold some gold in your hands. It's kind of amazing. But they're going to be grouped in the columns in which they're going to behave both chemically and have similar chemical and physical properties. These are going to be the transition metals, and a little bit later we'll see why these are kind of cumbersome. They don't always behave nicely. Kind of a goofy fact about me: when my daughter was born, I wanted to name her Nickel, and when my son was born, I wanted to name him Cobalt. My wife said, "No, I don't think so." I thought that was kind of cool. Those are the elements I got my master's with. Anyway. And after I got my doctorate, I worked with femtosecond chemistry, and I wanted to name my daughter then Femto. But my wife said, no, we're not going to name her Femto. It's kind of funny, isn't it? Oh, really, both parents are chemists. It's kind of nerdy, right? My wife did want to name her daughter Argento, which is the Latin word for silver. But I couldn't spell it, so we didn't do this. Come on, you can laugh, right? Listen, all right. You'll find out I do enjoy laughing. I do have a sense of humor, and it's shocking, but there is one there. So this is going to be atomic number. This is going to be the atomic weight. All right, so let's go do one more of these examples real quick. I'll put this over here. So in this case, this is going to be potassium 40. Now notice the weight does not have to match the weight on the periodic table. This is just going to be one of the isotopes. All right. This is a very unique isotope. My father is a retired math and physics teacher. He taught for 40 years at the high school level. And he taught up in Minnesota for 20, 22 of those years, something like that. And he would take his physics class every year up to the nuclear power plant. There's a nuclear power plant up there in Becker, Minnesota. And at that time, this is before 9/11, which you don't remember, that was before you were born. They would let classes go into the nuclear reactor building quite a bit. And every day, if you worked at the nuclear power plant, what they would do is they would measure the curies, or the amount of radiation you had when you went in, and then they measured the amount of radiation you had when you left. Does that make sense? Because they want to make sure you didn't get a shot of radiation. So I had my dad walk in through this Geiger counter. I said, "Oh, here, Mr. Neidiger, eat this banana." So he ate the banana and he set off the Geiger counter because a banana has some potassium 40, which is radioactive. Kind of cool, huh? What do you think it has a higher risk of cancer? Obviously, you'll guess this because of the question I asked. A stewardess on an airplane, or somebody who works at a nuclear power plant? Stewardess on the airplane. Yeah, stewardess on the airplane. You wouldn't think so, right? But they're flying so high up there that the only thing that protects them from UV rays is going to be that thin sheet of aluminum, right? So it turns out that stewardesses, or people, or pilots or whatnot, who are stewardesses, pilots who are typically on airplanes, are going to have a higher risk of cancer because they're flying so high up in the atmosphere. They have a greater exposure to UV radiation, as opposed to somebody who works at nuclear power plants. So how many protons will potassium have? 19. And if it's a neutral species, how many electrons? 19. And then how many neutrons? 1. Make sense? We're good with these? Mm-hmm. All right. Now, the interesting thing is since this atomic weight is really the sum of the protons and the neutrons, why do we have these decimal points? Why are they there? Well, those decimal points are there because of what's called a weighted average. All right. Now, before we get to there is a unit, a very, very, very small unit, which is called the atomic mass unit. Now, in science, we have this law, which is the conservation of mass. Mass is neither created nor destroyed. And that actually occurs in chemical reactions as well, too. So if we were to actually do a reaction, we don't want to count the number of atoms. So a way to get around that is to look at this thing which is called an atomic mass unit. Instead of having to count atoms, we can actually use mass. Now, this will eventually get us to this thing called a mole. A lot of you have heard the term the mole. So 1 atomic mass unit is going to be equal to 1.66054 times 10 to the minus 24 grams. To let you know, I have not memorized this number. Right, so it's not used that often. The best place that this unit or this unit or this number is used is if you're talking about nuclear chemistry. So we don't use that number very much. Or we can say that 1 gram is going to be equal to 6.022 times 10 to the 23rd AMUs. Have any of you ever seen this number before? Yeah, that's a pretty popular number. And if you had any good chemistry teachers, on October 23rd, they would have celebrated Mole Day, right? We'll talk about that a little later. But this is the number of atoms in 1 mole. We'll get to that in a little bit later. We won't do that right now. But the AMU is going to be based off the carbon-12 isotope, and it has the exact mass of having So one carbon-12 isotope atom is going to have a mass of 12 AMU. Right? We don't use that unit very much, so I don't get hung up on this. We won't use that a whole lot. You can use it quite a bit in nuclear chemistry, but not, like I said, we won't use that number very much. So we look at carbon, right? If you look at the periodic table I gave you, you'll see that the mass of carbon is going to be 12.01 AMUs. Now, why is that the case? Why does that exist? What seems kind of silly. Well, that's because 98.93% of all carbon that we have been able to measure is going to be of the carbon-12 isotope. A little over 1% of all carbon that we've been able to detect is going to be of the carbon-12 isotope. Okay. Now, this is going to be the percent in decimal form of the carbon-12 isotopes. All right. So we multiply that plus the percent times the mass of the carbon-13 isotope. All right. If we do the average, do this arithmetic, we come out with a mass of 12.01 AMUs. If you look on the periodic table I gave you on Friday, you'll see it. That is the number below the letter C. Okay. So that's where that number comes from. That number at the very bottom of the periodic table is what's called a weighted average of all the isotopes for potassium in this case, or all the isotopes for carbon. If you're looking for hydrogen, you'll see it's going to be 1.008. That's because that's a weighted average of all three isotopes of hydrogen, the tritium, and the deuterium. Does that make sense? So that's where that number comes. That's what that number is. You good? Yes.
Why is there a 0.00335 after the 13?
Oh, that's a good question. You mean here?
Yeah.
That happens to be the weight of the carbon-13 isotope. Why is it there? I don't know. It's once you start getting into that realm, the mass is a little bit different. It's just to give you an explanation. So let's say that we wanted to make a new element. All right. So what we're going to do is we're going to take an electron and we're going to get it going extremely fast. Right. This is a little strange. This is a rest mass, is what this is. The resting atom sounds really kind of strange, but if you take that electron and you start, at Argonne National Laboratory, just south of Chicago, we'll do this. They'll take an electron and start whizzing around a donut. I believe either diameter or the radius is 3 miles. So it's a perfect circle. So they'll get this electron and actually get it going extremely fast. As that electron starts to approach the speed of light, guess what happens to its mass? It starts to increase. As the mass increases, the electron actually starts to slow down because it can never quite reach the speed of light. So this is the resting mass of it. Because as it moves, the mass changes. Little bizarre, isn't it?
Yeah.
Yeah. So I mean, now this is perfectly defined as 12 AMUs. So that's why it's 12 AMUs, because we've defined it as such. But this is the actual resting mass of the carbon-13 isotope atom. Bizarre. Once you get to that area, everything is just different level. It's just all right. So let's look at magnesium. So magnesium has three naturally occurring isotopes. We have magnesium 24, which is going to have an AMU of 23.9850 AMUs, and its abundance is going to be 78.99%. We can also have a magnesium 25 isotope, whose mass is going to be 24.9858 AMUs, and its abundance is going to be, wow, exactly 10%. We can have magnesium 26 isotope, and its mass is going to be 25.98826 AMUs, and its abundance is going to be 11.01%. We want to calculate the atomic mass of magnesium. So how are we going to go about doing this? We're going to do it. It's pretty simple, straightforward. We're going to do the weighted average of all three of those isotopes. These percentages, if you add them up, are going to be 100%, which is what we want. Do the space on the board. We're gonna kind of do it vertical, all right? We're gonna look at the magnesium 24. So that would be 0.7899. That's gonna be our percent decimal form. We multiply that by our AMUs. For the most part, these are going to be given to you. I do not expect you to know these. All right. And so this would be 23.9850 AMU. We look at the next one, the 10%, so that's gonna be 0.1000 times its atomic mass, which is 24.9, what is that? 858. And sorry, I make a better door than window. You get it? I heard a lot when I was a kid. My dad would be watching football games. I'd be messing around in front of me. You make a better door than window, kid. 0.1101. That should be 25.9826. And we're gonna take those and we're gonna add them up. Okay. Four. So what I got when I did this arithmetic is I got 24.305. And what you got? Yeah. I look on the periodic table, look at my magnesium, or what it has here on the periodic table. Is 24.31. We're good. Yeah,
So you just multiplied the percentage of the animals and then for each of them and then added those together?
that's all I did. Yep, yeah, because all this number is simple. It's just a weighted average of all the isotopes that make up that element. It's actually, it's amazing. I didn't know this as when I was a student. I had to do this when I was teaching. You'd be amazed at the number of isotopes that these elements have. Just the sheer number. Gold, for example, has a lot of isotopes. You wouldn't think so because it's such a stable element. It's a tremendous amount of isotopes. It's absolutely amazing. Oxygen has a bunch of isotopes. Oxygen 18, and it's just amazing. All these different types of isotopes. I was just blown away. It's pretty remarkable. So a lot of them don't last very long. You know, you're talking milliseconds, just really short lived, but some actually are quite long. For example, if you look at bromine, I mean, it's an interesting element. It has a molecular weight of 80. Bromine 80 doesn't even exist. It doesn't exist. So bromine's molecular weight is 79.90. So basically 80, right? Bromine 80 doesn't even exist. All bromine is really 79 and 81. And it's a 50-50 mix of both of them, which gives you a lower mass of 80. But bromine 80 doesn't even exist. I mean, I find sorry, I'm nerding out. I find that really amazing. I find it so cool. Yeah, it doesn't even exist. I'd like some bromine 80. Oh, good luck. You can't get it. You either get the 79 or you get the 81. You can't get the 80. Which is amazing thing. So that's kind of cool. It's just not stable. It's just not stable. If we have time, I don't know. Second semester is a little bit harder than first semester. But if we have time, we'll end with nuclear chemistry. And you'll see that there's got to be a certain ratio of neutrons to protons in the nucleus, or the element just isn't stable. So it just isn't even stable. And they haven't even, as far as I know, I don't think they've even discovered it. It even exists at this point. It's kind of cool though. All right. I don't know why I have another picture of the periodic table, but I think it's pretty amazing. This black line here is what separates the metals from the non-metals, and as I said, to the right-hand side is going to be non-metals, the left-hand side is going to be metals. This becomes important later on because I'm going to try to give you some clues as how to solve problems with the periodic table. Yeah, it's absolutely amazing. I absolutely love it. We'll get into next chapter when we talk about periodic trends. We'll really get into this a little bit more. Uh, any questions up to this point? Yeah.
Up and down, or what are they? Is it rows is this way, columns is this way?
Yeah, columns are going to be vertical, rows are going to be horizontal. So the columns have similar chemical and physical properties. And we'll see it. So when we start looking at ions, these will all be +1. These will all be +2. These are going to be +3. Don't tell Dr. Baldwin I said this, but we'll look at these as +4. That's really not very accurate. These are going to be either +5 or -3. These become -2, -1, and 0 when we look at those ions. We'll deal with the rows when we do what's called electron configuration. We'll look at those. We'll start worrying about the rows then. We look at some of these periodic trends. We'll look at the rows then, but what becomes important is that the vertical trends of these, that they have similar chemical and physical properties. Yeah. Good? All right. So as I stated, at the very end of the semester, your final is going to be the American Chemical Society exam. I will put I don't know where this came from. If you try to Google those questions, you can't find them. That exam is written and housed at Iowa State University in Ames, Iowa. And I swear those people must have graduate students surfing the internet looking for photos of that exam. It's very difficult to find copies of that exam to study. So I have assembled some multiple choice question exam. I'll put that on Brightspace today. But I've also written some example questions here. Now that exam is going to be about 50% theoretical and 50% calculation. Now the calculations, most students do really well because I absolutely love math, and so I tend to favor that, but I'm trying to do more theoretical. The problem with theoretical questions, though, is you have to read the book. I can't give you all that information. Does that make sense? So I've tried to put some theoretical questions here, and anything you see as a multiple choice is something that should hopefully help you with such questions. Does that make sense? But I have assembled some. A friend of mine gave me a bunch of questions he used to help his students with studying for that exam. So, under standard conditions, most elements on the periodic table are A gases, B liquids, C nonmetals, D solids. I'm deaf. You got some, yeah.
Solids.
Solid, yep, most of them are solid, right? Yep, yeah, right here. Right, so look at the particle, these are gonna be solids. These are gonna be metalloids, these are gonna be your non-metals right there. So most of the elements on a periodic table are solids. Yeah,
One question about the quizzes before the exams, are they just gonna be built like the exams? And
it'll be 10 questions. I'll take one big question, a big overall theme of each chapter, put that on the quiz. So the idea of the quiz, I know you want to hear some, but the whole idea of the quiz is to humble you. To kick you in the rear and say, I need to start studying now, as opposed to delaying and waiting till the last minute. I know this will shock you. I was not a good student. I messed around a lot. And so my GPA was actually pretty pathetic in undergrad. But when I went back to graduate school the second time, so I got my master's, and then I went and worked for 5 years, and then I married this amazing woman, and her parents didn't send her over here to marry some slacker like me. They sent her over to get educated. So after our first year of marriage, we said, let's go get our PhD together. Great way to start a marriage. She's Miss Goody Two Shoes and really smart. But what I ended up doing is I studied every day. So I would always get stressed the night before the exam because I was trying to learn the stuff the night before the exam. And I remember sitting at a in a little apartment we had in Coralville, Iowa. And my wife said, "You Americans don't know how to study." And so she literally sat there that day and taught me how to study. And so I went from a 2.6, which was what my GPA was as an undergrad, to a 3.5 in graduate school. And I learned to study every day. And except I would take Friday nights off and Saturday nights off. But I studied every day. And just and it didn't matter what the topic was. Whatever it is, I just studied it. And I usually, so for example, what I would do if I were a student today, I would then, if I didn't have class, I'd go and I'd study this material until I had it mastered that day. That makes sense? And so that's a good way to study for that exam. I would read the book, I would take notes, and I always studied by myself. And I didn't have cell phones, but I can't study with a cell phone near me. So after this class, if I don't have any questions, I do have to go study actually. I'd rather have, but that's how I study. So I just sit there, I do it every day. It's consistent every day. Every day is what I do. Makes sense. So if you struggle studying and you're having a hard time with your grades, and another thing I do, the biggest thing I did is I didn't care about the grades anymore. So as an undergrad, I really cared about my grades, and it's kind of funny. I did really bad when I went to graduate school, which I quit my job. I had to stay in the graduate school for us to do this, for both of us to do this. I didn't care about my grades anymore. I just cared about mastering the material, and then I figured the grades would take care of themselves. And I didn't do the whole thing, well, do I need to know this for an exam? I never asked that question. I quit doing that. I quit guessing because I'm not very good at guessing. I just said I'm going to learn it all. And if there's something I'm kind of short of, then I'll make it up for the other things. So I never cared if this is going to be on an exam. I just said I'm going to learn it, learn everything. And that helped out. And I looked at studying not as a, hey, Paul, I didn't study. I didn't look at the stuff as oh, this is school. I looked at it as a job because I've always enjoyed work. So I just kind of played little mental games in my head. Does that help you out? So if you need help studying, let me know, all right? When I graduated high school, my math teacher said I was too dumb or stupid to go into math and science. I just knew that I was. Oh, yeah, it made my folks proud. And actually, when I went to get my doctorate, my parents weren't very happy. So I did. But anyway, that's to help you out. So consistently just do it and then read the book because that's how you get all that theoretical stuff. And I always say this, if you really do terrible in this class, some people do. You go, oh, this is whatever you get in the final, I'll give you that grade. I mean, if I had a student that I won't tell you his last name, he never went to school here. He was a student of mine a long time. His name was Zach. I'm not gonna say the last name, but he was of a particular athletic group that typically didn't do real well in my class. And he was at a D minus type thing coming into the final. He got the highest score in the final I'd ever seen. He finally woke up, finally studied. So he got an A in the final, and I gave an A for the class. And now I think he's a physician, and he went and became a doctor. So he finally just kind of woke up. So I'm going to study now. So whatever athletic event and consuming copious amounts of alcohol, I'm sure he was. He just quit all that and started studying. Had a D minus, D plus in my class, and got about 50 on the ACS exam, right? So he got an A. I didn't care what happened before that. So I always throw it out to the students. All right, we're good? Does that help you out a little bit? So Logan chemistry never came naturally. It was always hard. It's always been hard. Now, we're going to talk about this a little bit more in the next chapter, but there's a couple of ways in which we can write chemical formulas. One is we can write the molecular formula. This is going to contain the actual number of atoms that make up that molecule. Or we're going to write the empirical formula, which is going to be the relative number. So if we have glucose up here, which is a sugar, we can see that the molecular formula is going to be C6H12O6. The empirical formula, if we take the relative numbers into account, we see that there are twice as many hydrogen atoms as there are carbon atoms, and there are twice as many hydrogen atoms as there are oxygen atoms. So the ratio between these is going to be carbon to oxygen is going to be 1:1, and the hydrogen is going to be 2:1 and 2:1. Now, these subscript down here is going to indicate the number of elements in this molecule. So this molecule of glucose is going to be C6H12O6, which means it's going to have 6 carbons, 12 hydrogens, and 6 oxygens. Does that make sense? We will learn how to calculate molecular, first empirical formulas and then molecular formulas in the next chapter. Now, some atoms do not occur as monoatomics. They're going to appear as diatomics, meaning they're in the molecular form or in their elemental form, they're going to be 2 atoms bonded together. So, for example, hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine are going to be diatomic in their most elemental basic form. You're going to have 2 hydrogens, or you're going to have 2 oxygens, you have 2 nitrogens, 2 fluorines, 2 chlorines, 2 bromines, 2 iodines. And this is free. I'm not going to ask anything on this, but this is just some of you want to be chemists. Phosphorus, for example, actually appears as P4 in nature. It's not just phosphorus by itself, it's going to be 4 phosphoruses. And something even more amazing, sulfur is going to appears as S8 in nature. So it's octaatomic. Right. Everything else, carbon is just going to be 1 carbon, or gold's going to be 1 gold, or aluminum's going to be 1 aluminum. But some of these do not occur that way in nature. So far, so good? Make sense? All right. So which element does not exist as a diatomic molecule at room temperature? So go back to this list. We have hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. Which one here does not? A. Yep. Arsenic. Yep. So arsenic doesn't. So it'd be A. So far, so good. Just there's got to be some memorizing in this class. I try to keep it to a minimum. Which is not an empirical formula? B. That is correct. Yep, B. Everybody see that? Because we can simplify this, correct? We'll look at the empirical formula. The empirical formula is going to contain only the relative numbers. And notice how this is really simplified, right? So we have C6H12O6, right? We can simplify this if we divide both of them by 6. We get CH2O. So clearly this is going to be, that's an empirical formula. This one's going to be an empirical formula. That one's going to be an empirical formula because I can't simplify them anymore. But this I can simplify. So that is going to be, this is going to be the molecular formula. I will say on that ACS exam, there are questions that are tricky. That I'm not going to lie to you. I'll take it with you, and I always miss 1 or 2 on that SOE exam. I don't know why in a hurry. But we'll talk about that a little bit later. And I'll put that practice exam up there for us. All right, we're good? All right, now I know you are thrilled about this. But if these elements did not form ions, we'd be done with chemistry class. You wouldn't have to get up and be here at 7:45 in the morning. And I know you're glad they do this. Because we love 7:45 classes, don't we? That's amazing. Wow. Turns out that what these elements can do is they can actually bond. Now, in order for them to bond, we're going to look at the simplest, all right? And that's what this whole year is going to be about, these ionic compounds, compounds. Now, those who take organic chemistry, that entire branch of chemistry looks at a different class of chemicals called covalently bonded or polar covalent compound. In this year, we're going to be looking most at these ionic compounds. So what is an ion? An ion is going to be an atom that loses or gains an electron to become a charged species. Okay. And this is going to be written as a superscript. Okay. So a cation is something that loses an electron. If it loses an electron, is it going to be positive or negative? It's gonna be positive because it's giving up something negative. Does that make sense? It still has the same number of protons. Still has the same number of protons. If it were neutral, it would have the same number of protons and electrons, but if it gives up an electron, it has fewer electrons than it does protons, so it's still going to be positive, right? When I was learning this for the very first time, how I remembered it is I sort of see a positive in here for cation. Make sense? An anion is going to be a species that gains the electron. If it's a neutral species, it had the same number of protons, the same number of electrons. But if it gains an electron, something that's going to be negative, it will become a negative species. So for example, what we have here is we have sodium, which as a neutral species will have 11 protons and 11 electrons. It loses an electron, and so therefore it has one more proton than it does an electron. So the species itself will be positive. Chlorine here will have 17 protons and 17 electrons. It will gain that one electron from the sodium, and it will then have 18 electrons and 17 protons, so it becomes neutral. This positive cation and this negative anion, because of electrostatics, will then bond, produce an ionic bond. Make sense? Some interesting things about ionic compounds is that they're typically very brittle. They typically have high melting points. They do not typically conduct electricity in their solid form. Now, when they're dissolved, they will conduct electricity. And so ionic compounds that contain a positive cation charge and an anion, which would be a negatively charged, they come together. So we see this sort of in this example. We can look at table salt, in which you have sodium, which will have 11 electrons, 11 protons. It loses that electron to the chlorine. We'll learn in a few weeks why it does this, why sodium is so willing to lose that electron, and why chlorine is so willing to take on that electron to produce these two ionic species that will then bond together to produce sodium chloride. But that's what happens. This sodium will very willingly and gladly give up the electron. This chlorine really wants that electron really bad. And so they form an ionic species. Does that make sense? Some common ones we see every day are sodium bicarbonate or baking soda, HCl, hydrogen chloride, calcium carbonate, ammonium nitrate. These are all going to be some type of ionic compounds. Okay. So here we see our periodic table again. So how do we know the charges of these ions? This column here is going to form a +1 charge. All right, we're going to go over this a lot. This will form a +2 ionic charge. So these are going to be the cation. These are going to be the transition metals. These charges vary. All right. So for example, iron can have multiple charges, right? It can be +1, +2, +3. It can have multiple charges. It doesn't have just one fixed charge. So they vary. Cobalt can have multiple charges. Nickel can have multiple charges. However, zinc only has one charge. It's a +2. So it's hard to read. So we'll talk about these a little bit later about the charges of some of them. And once we get into electron configuration, then you're, oh, I understand why these have multiple charges. These will be +3. For the moment, we'll call these +4. That's not a very accurate statement, okay? These can be +5, but mostly they're going to be -3. These will be -2. The halogens will be -1, and the noble gases will have 0 charge. This is why they're called noble gases, because they don't form ions. They are not charged. And so what does nobility do? Nothing, right? They do nothing. Right? Isn't King Charles the King of England right now? I think he is. He does nothing. And then his son, William, I think he's the next one in line. Because the other one lives here in America, I think. And they got booted out of the family. But so they don't do anything. Prince King Charles is a billionaire, has never worked a day in his life. He's- So these typically don't have it, they do not react. Now, that's not entirely, xenon does react, it does form compounds, and it's actually. The compound, if one of the compounds it forms is actually used to deliver epileptic medicine to where it needs to go into the body. It's kind of cool. But for the most part, these do not react. Any questions on that? So we'll do that again. These are gonna be +1. These are gonna be +2. These over here are gonna be +3. We'll call these +4, but that's not very accurate. We'll look at these as -3, -2, -1, and then 0. Okay, those would be the charges, right? So +1, +2. These have multiple charges. These would be +3. For the moment, we'll look at these as +4, -3, -2, -1, and then 0. Good? All right. All right. Okay. Now I think there's really two tedious things in this entire semester. One of them is what we're going to talk about next. I think it's exceedingly tedious, meaning boring. And then we'll do stoichiometry, and that's pretty boring as well, too. It's easy, but it's boring. So we're going to do nomenclature. So nomenclature is how you name something, right? We're going to be looking at the inorganic naming classification. Those of you who take organic chemistry next year, that's a little bit more complicated. All right. So we're going to look at very simple binary metal, non-metal compounds. Okay. So binary ionic compound is going to be composed up of two elements, one cation and one anion. Right. And if we do a metal, non-metal, the cation, so the metal, will just preserve or keep its name. The anion will have a special ending. The anion will end in "ide." So, for example, this would be sodium chloride, calcium oxide, and this would be magnesium nitride. So the metal is typically going to be written first. Notice the metal is written first in all of these. So the sodium is the metal, the chloride is going to be the non-metal, so the metal is written first. Calcium oxide, the metal is written first, and magnesium nitride, the metal is written first as well, too. Makes sense? It's by convention. If you get it wrong, I'm not gonna mark it. No, don't worry about it, right? As long as you get the charges right, that becomes a hard thing. The charges is what becomes difficult. Yep, yep. Now, if you misspell it, no big deal, as long as you're pretty close. Far so good. We'll look at a little bit more of these a little more carefully. Okay. We look at sodium chloride, right? And if you look on your periodic table, what would the charge of sodium be? Look at what column it's in. Which column is it in? +1. Yep, so the first column would be +1. If you look at where chloride is, what would the charge of the chloride be? -1. So notice that we have one sodium for one chloride. That makes sense? let's go down and if we look at calcium oxide, right? What's the charge of the calcium cation? Plus two, it's in the second column, right? It's in the second column. So it's gonna be plus two. What's the charge of the oxygen?
-2.
-2, yeah. And you would sort of know that if you already know calcium is plus two, you got one calcium on oxygen, so that tells you oxygen's gotta be -2. Makes sense? If you look at magnesium nitride, what's the charge of magnesium? No, of magnesium. So it's gonna be in the second, yeah, it's in the second column, so it's gonna be +2. What's the charge of the nitrogen? -3, that's gonna be -3. So in order to get this to be neutral, right, you look at the least common multiple, remember that? The least common multiple between 2 and 3 is gonna be 6. So if we have 3 magnesiums, this is gonna make it +6. If we have 2 nitrogens, this is going to be -6. So this half is +6, this half is gonna be -6, so it's neutral. Now, a little cheap, it doesn't work always. It doesn't always work, it works most of the time. Is that this charge, whatever that is gonna be the number of the anion. The charge of the anion is gonna be the number of, oops, a little bit better. Is going to be the number of cations that you need. Does that make sense? That doesn't always work. There are a few exceptions to that. Which is what you're gonna find out about chemistry, which makes it kind of frustrating at times, is once you get comfortable with it, oh, we got another exception. Make sense? What would I name this compound? Lithium bromide, yep, that's exactly right, so this is gonna be. Gonna be lithium bromide. If I wanted to write the chemical formula for calcium chloride, how would I do that? What would I do is I would write the symbols down. So it'd be Ca, right? And then chloride is Cl. So that'd be the first thing I would do. The next thing I would do is I would look at the charge. So the charge of calcium is how much? +2, that's exactly right. So that's going to be +2. What's the charge of the chloride? -1, exactly. And so to write this, it would be CaCl2. That makes sense? Any questions on that? Yeah.
You don't put the one there, but it's just one, right?
No, yeah, I don't leave, yeah. If you put a 1 there, Ray, it's not the end of the world. I'm not. By convention, you typically don't, yeah, just leave it alone. Let's look at another one. Use sodium oxide. So charge is so the symbol for sodium is Na for natrium. So the Na and then oxygen is just going to be the O. Right? What's the charge of sodium? It's going to be +1, exactly. And the charge of oxygen is going to be -2. And so to write this as a neutral species, it would be
Na2.
Na2O. Exactly. Na2O, exactly. Make sense? Oh, here's a good one. Aluminum oxide. which is a really neat compound. I have an aluminum fishing boat and my hull is very gray. It's because it's coated with aluminum oxide. And this stuff is almost perfectly chemically inert. It's just absolutely amazing stuff. I do remember that a long time ago, I lived up in Minnesota and I worked with this guy and he had a brand new pontoon boat and every fall he'd polish and buff the pontoons. I said, why are you doing that? This stuff is, it's so inert. It can't react with it. He wanted it to look shiny. So aluminum is what symbol?
Yeah.
Al, yep, Al. Oxygen is gonna be O. What's the charge of the oxygen, or I'm sorry, charge of the aluminum?
Plus
Three. It's gonna be -2, so how to write aluminum oxide?
L2.
Yes, 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 you know, 2, O3.
Yep.
Easy? Yeah, you just want the charges to be balanced, that's exactly right, you want this to be neutral, that's it. You do a little math arithmetic, a little math gymnastics in your mind and try to get that thing to be neutral, that's the whole goal, yeah.
Then what happens when you have one in the lake?
Oh,
That-
you had to ask, didn't you? Oh, my goodness. Life was so simple now, wasn't it? Just easy. Well, we'll get to that on Wednesday. Does that make sense? Because we don't,
That's fine.
well, I'll tell you exactly what happened. You gotta write the charge. So I'll do it real quick. I'll tell you what, here's how so they have multiple
Sorry.
charge. No, you can't. Because after this slide, after this slide, because this is easy. Why? I thought I had one on here. You got that? Oh, there we go. Uh. Yeah, sorry, before. We gotta put the Roman numerals in for charges. So for example, if you have this. Right? What you have to do is you have to look at the anion first, because they always tell you the truth. The cation always lies to you. That's how I kind of figure it out. This will be, remember, chloride is gonna be -1,
Oh, so it's just-
so iron's gotta be +3. You see, right, this is iron. 3. So that,
Yes.
but iron can also be this, there's no reason it can't be that. And so this would then be the iron 2. Alright, the Roman numerals. This is equal to the charge. Not the number. Mikey. It's equal to the charge. And that gets confusing, my friend, because what we're gonna go to on Wednesday is once you do non-metals, then you start counting up the atoms. So it gets kind of confusing. So that's why I apologize, but I put a lot of emphasis on the periodic table. The first thing I do is when you have to name something or write the symbol, look at where it is on the periodic table. Wherever it is on the periodic table, that will determine or dictate the rules you have to follow. That make sense? All right, well, cool. Have a good rest of your week, and I'll see half of you tomorrow morning.